Som, teste. Olá, boa tarde. Sim, tudo bem? Acontece. Sim, tudo bem? Sim, o prazer é todo meu. Eu sou engenheiro eletricista. Eletricista. É, pois é. Ah, que legal, que legal. Eu acho bem legal também. Ah, tá. Sim, pois é. Bom, o professor Claudio e a professora Mercedes também me parece que tem uma formação bem diversificada também, né? Sim, legal. Sim. É, bom, acho que ela pode falar melhor, mas ela fez, acho que mais de uma graduação. Inclusive, eu acho que ela fez uma graduação no Rio, na PUC do Rio, depois que ela foi para os Estados Unidos. Desculpa? Ixi. Ah, ok. Temos o Marcelo, vamos ver. E temos o Claudio. Olá, olá, tudo bem? Eu não sei, vocês estão me ouvindo bem? Olá. Ah, tá bem. Vocês me ouvem bem? Só para eu confirmar? And maybe we have just. Sim. Acho que sim. Hello, Marsh. So just to inform all of you, we are already on YouTube. Yes, back. Okay. Okay, thank you, Marcelo. And so, first of all, I would like to thank all professors that accepted this invitation to be here in this committee evaluation for my PhD thesis. So this this thesis is presented to the Institute of Biomedical Science of the University of São Paulo. And I was supervised by Professor Marcelo Urbano, who just talked now. I will present my work. The work is entitled Risk Heterogeneity in the Modeling of Infectious Disease, a Malaria Study Case in the Amazon Basin. So let's start. So I'm gonna just give you a brief introduction about the topic I will discuss and tell you about the material that we used in 3 different articles. So the results and discussion will be presented in 3 different sections. Yeah, so we have one article where we did the statistical modeling, the second article where we did the mathematical modeling of malaria transmission, and the last one where we did survival analysis, all regarding malaria in the Amazon basin. In the end, I will just give you final considerations. So let's start with the introduction. Since at least since 18th century, mathematical models have been used to study transmission dynamics of infectious disease. By that time, Daniel Bernoulli, he just presented one article where he tried to answer one question. His question was, should the voluntary inoculation of a small amount of less virulent smallpox be encouraged, even if it's sometimes a deadly operation? So then he created a mathematical model. He made some simplifying assumptions. He defined some variables and some parameters. Next, he estimated the parameters that he defined previously. He made some simulations, and then from the simulations, he could interpret. He could try to answer the question that he posed at the beginning. So he just considered that amount of people, the population was susceptible to smallpox, then they would get infected according to a rate, and then they would recover. Some would die with a higher probability than if you were not infected. So then later on, in the beginning of 20th century, Ronald Ross and followed by many other researchers, they started to model transmission dynamics of vector-borne disease. He had also a question at that time, and then his question was, does malaria could be eradicated simply by reducing the number of mosquitoes? So he also created a model with the same procedure as we saw before, but his model also considered compartments for mosquitoes as well. It was a bit different model than the previous one. So in the end, we saw the same structure in order to apply mathematical models to infectious disease. Yeah, and this is followed until nowadays. Yeah, so you observe the nature and formulate a question, then you pose some simplifying assumptions, you define variables and parameters, you translate all these into mathematical equations, then you estimate your parameters and you make simulations. Sometimes you have to go back and change your assumptions or change your parameters or variables, but the flow would be more or less like this. So both Bernoulli's and Ross McDonald's model, they had a common assumption. Yeah, they assumed that the population was homogeneous. Yeah, the population risk was homogeneous. But as the science was evolving, and many results was coming up, we learned with time that the population is not exactly homogeneous regarding to risk. There is individual variation, and this individual variation can be divided into different classes. We are saying here. So we can have individual. Eu não estou compartilhando minha tela? Me desculpa. Do meu microfone. Ok, eu vou tentar falar mais perto. Não, eu que peço desculpa por não ter transmitido. Eu acho que no YouTube já estava transmitindo, aqui não estava transmitindo. Peço desculpa. Ok. Tá. Okay, I'm so sorry. Can you just confirm that you can see my screen right now? Okay, I'm so sorry. I'll just show the slides and not talk again. So introduction, then Bernoulli's model, Ross McDonald's model, then the flow to make mathematical modeling, and then here we are. I'm so sorry. So let's go again. And I'll try to be a bit slower. Yeah. So as I was saying, both models had the same assumption. Both assumed that the population was homogeneous with regard to the risk. Yeah, and we can divide this risk in two different classes. We can say that individuals, individual variation can be heterogeneous in exposure or in susceptibility. Yeah. So what I mean about exposure? So we may have some spatial heterogeneity. We may have control measures that are applied in one place and in another place not, or even people using properly or not the control measures, for example, bed nets in the case of malaria, and other exposures. We also have variation in susceptibility. The clearest example is vaccination. Yeah, if you are vaccinated against a disease and the vaccine is efficacy, then you have lower susceptibility to get infected or at least to develop a disease. Sometimes it's not immunity against infection. But anyway, you also have partial immunity, cross immunity, and so on. So then I would say we do not have problems about saying that any population is susceptible of susceptibles is heterogeneous with regards to the risk of infection. So this was already seen in the literature. There is this classical article where where the authors could see for different infectious disease that more or less 20% of the population is responsible or contributes at least 80% of the net transmission. Yeah, so it's basically saying that a small amount of people is responsible for the majority of cases for many infectious diseases. This was already seen for malaria in Africa. So they also saw that 20% of people received 80% of all infections in this study, how it's reported. So regarding modeling, there is this article, very dense article, mathematical one, which Professor Claudio is co-author, and it's really nice paper, which shows that if you consider heterogeneity in the population, and the heterogeneity here expressed by this delta here, for different levels of heterogeneity, we have different patterns of here proportion of infected people for a given infectious disease. This was also seen by Vaupel and his colleague in survival analysis. If you have a population composed by a group of two subpopulations with different risks, and here he's talking about mortality, the observed hazard rate for the entire cohort is different from the respective subpopulations. Given this framework, this introduction, our research hypothesis here is that risk heterogeneity should be accounted for appropriate statistical and mathematical modeling of infectious disease. Here we are going to use real data from the Amazon basin. Then our aim is to investigate the risk heterogeneity in statistical and mathematical modeling of infectious disease using malaria morbidity data from the main urban transmission hotspots in Brazil. We have 3 objectives. So we want to characterize the malaria risk heterogeneity by identifying risk factors. Basically, we're going to do regression analysis, and then we are going to, our second objective is to design and calibrate, do all the process for a mathematical modeling model describing the transmission dynamics of malaria in the same area. And in the end, we will try to integrate risk heterogeneity in survival analysis as well. So here we try to investigate the risk heterogeneity. Before starting modeling any disease or any biological event, we have to understand a bit of its biology. So here, very briefly, so mathematical is malaria is a vector-borne disease. We have 2 cycles in the transmission life cycle, one cycle in the man or in the vertebrate host, and the other one in the mosquito. So the infected female mosquito injects an sporozoite which will flow until the liver, and the liver will differentiate until it becomes merozoite, and then it goes to the blood, where it's going to invade red blood cells. In red blood cells, it's going to differentiate until the rupture of the red blood cells, and the merozoites leave it in this stage. The majority will invade new red blood cells, and others will differentiate into gametocytes and will infect mosquito again, the female mosquito after a bite. Yeah, inside the mosquito we also have this part of the cycle. So Plasmodium vivax, which is the main Plasmodium in America, has this ability to be in the dormant stage, the so-called hypnozoite following primary infection, and it can relapse over the next weeks or month. Because of this, radical cure is required. So hypnozoitocidal drug is combined with isontocidal in this case. Then also the epidemiology in Brazil, just to know where we are. So malaria in Brazil is mainly concentrated in the Amazon basin. It's a notifiable disease, and malaria just can be diagnosed and treated in the public health system. The majority of cases, as I already said, is due to P. vivax, and we also have P. falciparum. During the last decades, the number of cases has dropped considerably. So, material. Can you confirm just that you are listening correct, please? Okay, so I'll keep going. So, which material do we use? So, we used 2 different data sets. We used a population census that was performed during November 2015 until April 2016, where all the inhabitants of Mancio Lima, located here in the Acre state, also in the Amazon basin, where it was collected individual and household information. We combined this data set with the data set from the Ministry of Health, where all the cases diagnosed in Mancio Lima and also in the neighboring city was reported. Yeah, so we combined the malaria infections with the population census, and we performed the analysis. This is a photo of Mancio Lima. Yeah, so actually it was taken by myself when I was in the plane. We can see here it's not a big town, yeah, but it's we have some areas with higher density of people, yeah. And this one is the Cruzeiro do Sul, yeah. So we have the river here, the forests all around the forest. This one's a bit bigger. So then we start discussing our results and in the first article. So here I'm going to present you the article entitled "Statistical Modeling of Surveillance Data to Identify Correlates of Urban Malaria Risk, a Population-Based Study in the Amazon Basin." This is a cooperation work between the Institute of Mathematical and Statistics from the University of São Paulo and our Institute, Institute of Biomedical Science. Okay, so as malaria rates decline, as we saw in the epidemiological data from Brazil, so malaria count type tends to become more over-dispersed. And we can also find some subjects that are not infected for a long periods of time. So perhaps we have to include this phenomenon into our models to properly describe. Perhaps some people is not even exposed more to malaria, just some spots in the city or considering some behaviors. Yeah. Regarding malaria count type data, Poisson regression models are the most commonly used to make regression analysis and to identify risk factors. But it has a very strong assumption. It assumes that the mean and the variance of the distribution of count type data, yeah, is more or less the same, or is equal, theoretically speaking. Yeah. So with Poisson regression models, we cannot fit over dispersed data. A further challenge here is that, considering that we made a census in the population, people are clustered into households. Yeah. So because of this, they very likely share some common risk factors. Yeah. So to account for this clustering to households, we used random effects to account for the people that is not exposed anymore, or at least is not having any case of malaria during a long period. We are using zero inflated. And because our data is over dispersed, we are using negative binomial regression and analysis to try to identify the risk factors in this town. So here we had this distribution of malaria episodes per person in from January 2014 to September 2016. Yeah, almost 3 years. If I'm not wrong, this is 1,000 days. So we used this package, GANS, it's our package to try to describe this distribution. Our zero inflated negative binomial here just assumes that we have a proportion of the population having 0 cases that are free of risk, and then the rest follows this distribution. So the G here is going to be the binomial distribution. To select the models, we used archaic information criterion. We used 2 different diagnostics, model diagnostic, QQ plot and worm plots, and we used backward and forward stepwise selection for select the statistically significant covariates or risk factors in our regression. So here, what we found, we found that we had the malaria incidence density was estimated at 22.6 cases per 100 person years at risk. The majority of them was due to P-Vivax, and also the other part due to P-Falciparum. Our mean in our distribution of cases per person was 0.62, while the variance is 1.4. So here it justifies the use of the negative binomial distribution. And then here, without accounting for any covariates, we can see that the zero inflate negative binomial really matches our data. Yeah. So we had people having until 12 cases during this period. So we started with this random effect zero inflated negative binomial, but we didn't add n covariates to the zero inflated component first. And what we found? Yeah, so here we start looking at the QQ plot, yeah? And this diagnostic plot says that our regression should follow this straight line here. It follows quite well, the straight line, but here we had something that we were not happy with. Yeah, it looked like we had a systematic error. Then what we did, we look at the worm plot, and then here is more clear. Yeah, so we had this tendency here out of this band, which gives us the 95 confidence interval for the diagnostics. Yeah, and having this shape here, yeah, the interpretation of this shape, so worm has a negative slope, so here we have a negative slope, it means that the fitted variance is too large. To try to control this fitted variance, we went back to the random effect distribution. And then we tried to control the degrees of freedom of the random effects. By reducing the degrees of freedom of the random effects, by actually we were adding penalties to this to the random effects. We were in the end shrinking the distribution of random effects towards the mean, which here is the zero. By doing this, we had both diagnostic plots really well drawn. So here are the results of the regression. So what we have here, we have that people from 16 to 60 years old, they are under increased risk of malaria. If we have also the gender is related with the incidence. Here male, young adult male are under higher risk. We also found some characteristics of the house showing higher risk of malaria infection, as for example type of lavatory. If the house just have lavatories outside the house, which is quite common in that area, so they have outside they have increased risk. If it's inside, they are somehow they have some levels of protection. Yeah, but this is somehow already known. We know these characteristics from the literature. But then what we did next, we just plot, we had the GPS location of each household. And then we got the random effect predictors of each household, and we select the top 5% and the bottom 5%, and we just plotted here to see where they were located, just to see if we could find an area with higher than average risk of infection. we saw here, like the first look, we thought that being in the border of the city, yeah, so would be a risk factor for malaria in the area. While people living in the center of the city, they would have lower than the average risk of infection. Then what we did, what we wanted, how to systematically define what is the border and what is the center of the city. We used these alpha shapes, yeah. So we had the GPS location of all the households. Then we did this triangulation here. We could select the points in the boundary. We have to perform like different times this procedure, because if we had if we calibrate our selection of alpha shapes with not according values, we would have a lot of rows inside our data set. Around the city, yeah, sorry. Then we did this several times, and then in the end we end up with this, yeah? So the black points here are the boundaries, while the gray ones are classified as center. We add this to the regression, and we could see that this is statistically significant for the regression, and is showing one of the higher risk factors, yeah, living in the periphery of the town. So we had this, and this was selected to the regression. Then next, so far we didn't have add any covariates to the zero component, zero inflated component. But we could see just by the intercept that around 13.6% of the studied population were risk-free. So this was inferred by our last model. And how we asked, how can we try to classify this population? So someone can be risk-free if it's unexposed. Then for these, for unexposed people, we used the zone of residence. The people can acquire immunity over time. We used age and gender to represent the acquisition of immunity. And also, like, people can be naturally unsusceptible to infection. We didn't have any covariates to represent these events. So we add these three covariates into our regression, and then it was selected by the model. We had it was selected by the zero inflated part of the model. All of them, but sex, yeah, but gender, sorry, but the gender. So in the end, we had a better model regarding to the AIC value. So in the end, what we were discussing about these results. So perhaps, or very likely, occupational exposure reflects that young male are under higher risk. We are calling this hot pop, yeah, like the population under higher risk. We also could see that we had local transmission in the area, especially in the less urbanized periphery. Yeah, if we didn't have those variables wouldn't be indicate wouldn't indicate high risk for malaria in this case. And we also found a part of the population under no risk or risk-free of infection, as we assumed at the beginning. Great, so then we move to our next study. So here our study is entitled Modeling the Epidemiology of Residual Plasmodium vivax malaria in an Heterogeneous Host Population, a case study in the Brazilian Amazon. Yeah, so this study was done in cooperation with the Liverpool School of Tropical Medicine. Professor Gabriela Gomes had received me over there for this study. So then, again, we used the same material, but we excluded people over 80 years old because we had not so many points here. It was adding a lot of noise to our data sets. But here we just modeled 1 year, 1 year of the data set. We didn't use the whole data set. It was just 1 year closer to the census that was performed in this area. And then from the data set, we extracted these 2 data points. Yeah, so here we had the incidence density stratified by age and the number of cases per individual in 1 year. Yeah. So we tried to build a model to fit both data sets. And then when we were starting, we started with the simplest model we could use. And then we used just an SIS model. And with an SIS model, we just can fit the mean incidence density. So here is not what we were searching for. Then to try to correct this first, we add the age-dependent force of infection. Yeah, we saw in the literature many articles using this formula for the age-dependent force of infection says that the force of infection is correlated with the body mass, which means just if you have higher body mass, you have higher probability to get bitten by a mosquito. If you have lower body mass, you have lower probability. This is a curve like this. Yeah, if you are young, small, you have lower probability to get bitten than if someone is adult. All right, applying this age-dependent force of infection, we just could correct the first part. What is happening in the second part? The second part here, we hypothesized that some people were acquiring immunity to infection, and then next we added partial immunity acquisition function. This is described just by an exponential decay, which means that you started naive and then you get infected, you recover according to the recovered rate, and then you have the force of infection, which says if you're going to be infected or not again, but this is weighted down by the partial immunity. And here, in this case, 1 means that you just had 1 case. If you have more cases, you have more partial immunity. So then by applying this partial immunity factor, this is correct in the second part of the curve. So good, we're happy with this, but then when we look at to the distribution of cases per person, we could see that this distribution was not well fitted by this framework. So what we did, or what we thought could improve the distribution, yeah, or this fitting. we add this risk distribution. This is really simple. We consider that one part of the population is under low risk, which is given here by x1, and the other part of the population is under high risk of infection. This is just multiplying the force of infection, and also we keep using the partial immunity in our framework. So here we assumed that the risk distribution had mean 1, and the force of infection was controlled just by lambda and not by our risk distribution. Okay, so this is the end of the design, and then let's see how did we calibrate this model. So the model fitting, we just try to fit both data sets at the same time. Yeah, we assumed that the residuals were normally distributed for the age-dependent malaria incidence density, and also the number of cases per person, the distribution of number of cases per person. And then we have this likelihood. With this likelihood, we applied Markov chain Monte Carlo, but we didn't know which level of heterogeneity should we use it in that model. Throwing everything into the model and try to get the values for all the parameters, including the risk distribution, was not working. Then we optimized the model for different levels of heterogeneity. So we did, considering that 90% of the population was under low risk and 10 under high risk, 85-15, 80-20, 75, and so on. And the best model here, with the best likelihood describing our data, was the model considering that 80% of the population was under low risk and 20% was under high risk. So then with this, we could obtain the value for our parameters. Here are the optimization. They are, well, quite good, I would say. Also the likelihood really converged. And then here's our final result for this model. Yeah. So here we fitted the incidence density stratified by age. This was a composition of the high-risk population and the low-risk population, and the number of cases per person. Yeah, so here it's fitting quite well, I would say. And this was with this risk distribution, this force of infection, and this partial immune acquisition function, let's say, like this. So great. We just had this row here in our model, but we made one assumption, yeah? So if people are having lower chance to get infected as following repeated infection, yeah, previous infections, yeah. So let's say this guy is not moving to this compartment with this force of infection itself is weighted down by the partial immunity, but the partial immunity is not correlated with the number of bites or infected bites one is having. Yeah. So if this guy is not getting infected due to the partial immunity, he's moving to the asymptomatic compartment. It means that he would get a bite, but he would not get infected. Yeah, infected bite, sorry. He would not get infected, and he's moving to the asymptomatic compartment. So here we can see that this is complementary of this. Yeah, here we have sigma, and here 1 minus sigma. Just recalling that this is the partial unit function is an exponential decay with maximum at 0, and the maximum is 1. That's the reason we don't have anything here, because 1 minus sigma 0, which is 1, is 0, which means that if you are naive, you didn't develop any partial unit so far. Yeah, but here we had one problem. We didn't know for how long people would stay asymptomatic. Yeah, so he would stay here asymptomatic, and if he's not getting another infected bite, which is making him infected and symptomatic, he would become susceptible again after a while. Yeah, but for how long is it? We didn't know by that time, but we played with this value. Just showing here very briefly how is the dynamics for both groups. Yeah. So here, in the low risk group and in the high risk group, we can see that people is moving between compartments really slow, while in the high risk group, people are moving much faster. And the number of asymptomatic infections are just due to the high risk group. There's almost no one asymptomatic here in the low risk group. Here we just consider that one infected person stays asymptomatic for 90 days. And then here again we play it with that parameter. Yeah, so if we consider 30 days for that parameter, so all those numbers that we are imposing here was somehow based in the literature, but there is no consensus about this, especially in this area. Yeah, we use it 30 days. So with 30 days, we can see that the prevalence of asymptomatic infection is increasing over age, but increase more if it's 90 days or 180 days. One stays asymptomatic. Yeah, we can try to find this value for the whole spectrum from 30 to 180 days, and then by integrating these curves, yeah, if the average duration of asymptomatic infection is 30 days, we had the prevalence of asymptomatic infection around 1.5%. If it's around 180 days, it's around 4 or 4.5% of the population. All the asymptomatic infection in all the cases are mainly due to the high risk group. Okay, so then we simulated the proportions of infections that were symptomatic and asymptomatic. But for this, we had to consider a number of days in which infected and symptomatic infections would stay on, let's say like this, while for the asymptomatic infection duration, we also consider 30 and 90 and 180 days. So by considering 4, 8, or 12 days for symptomatic infection and 30, 90, and 180 days for asymptomatic infections, we could see that the majority of cases in the population, by assuming by considering our assumptions, was much higher than symptomatic individuals. But being asymptomatic, or let me change. So having higher proportion of asymptomatic individuals doesn't mean necessarily that they will contribute more to the transmission, because they can have lower probability to infect mosquitoes, yeah, because lower parasitemia, for example. So here again, we didn't know how is the relative contribution of symptomatic with respect with asymptomatic, or we didn't know this, and then we consider like half, 1/10, or 1/30. It means that, for example, 1/10, it means that one symptomatic individual contributes the same as 10 asymptomatic individuals, and the same for the rest. Here we can see that in many cases, asymptomatic infections are contributing quite a lot for the whole transmission. Yeah, if we get this value here in the middle, we can see that, for example, if we assume average duration of symptomatic infection as 4, so it is almost 60% of the contribution due to the asymptomatic pool of the population. So moving from here to here just means that if you make faster detection and treatment, you decrease the contribution of symptomatic infection, because here is just average of duration of symptomatic infections. Well, great. So what are our conclusions about this analysis? So here we can compare, and what we call the homogeneous model, which says that everybody has the same risk, with the heterogeneous model. Here the fit is better, but more than it, we have different inferences. We can see that if we use the homogeneous model, the acquisition of partial immunities inferred by the model is different from this one, and the conclusions would be different as well later on. We also could see that in our population, or at least in our inferences, we also found this 20-80 pattern. So in our case, 20% of the hosts contribute, the high risk ones, contributes 86% of the overall vivax malaria burden. So in this case here, they said population appears to acquire partial immunity slower than populations from high endemic settings. This was already seen as well in the literature. And as I said in the introduction, Plasmodium vivax, people having this infection may have relapse over time. Here we didn't consider relapses explicitly, but in our dynamical model, if we consider the risks, maybe this is underlined under the risk of infection. And the main conclusion of this work is like asymptomatic infections may constitute a major parasite reservoir in the area. Then, okay, last work. Let's go. Just a minute. So here, our last work deals with relapses. So it's entitled Quantifying and Preventing Plasmodium vivax Recurrences in Prima Queen Untreated Pregnant Women, an Observational and Modeling Study in Brazil. This is a comparison work between University of São Paulo and the University of New South Wales. So here, as I said before, Plasmodium vivax, which is the main Plasmodium in the area, requires radical cure, which is a combination of two different drugs. In Brazil, it's chloroquine and primaquine. So in this case, we did a retrospective observational cohort study, and in this study, we aim to compare the time to Plasmodium vivax recurrences following treatment in two different groups. In the primaquine untreated and the primaquine treated group. of course, we didn't selected people and didn't give Primaquine for them. Like pregnant patients here in Brazil are not, they do not take Primaquine, and then we compared pregnant patients with non-pregnant patients, and in a survival analysis to compare people treated with chloroquine and people treated with chloroquine plus Primaquine. So what we had, like what is our data set? We found 272 pregnant women with at least one Vivax malaria treated with only chloroquine, yeah, from January 2014 to September 2015. Yeah, okay. So then to increase the chance that this episode is actually a new infection instead of a relapse of previous infections, we excluded all patients who had any Vivax episode in the previous 6 months. Yeah. So because of this, because of this 6-month window, we could not select any patient here in the first 6 months. Otherwise, we could not guarantee this 6 month free of Plasmodium vivax clinical episodes. It's important to say that we are just doing with clinical episodes here. So in the end, we just had 200 cases, and then we tried to match the case with 2 controls. And so we tried to match considering the date of diagnosis. We just consider plus minus 30 days, sex, age, and the malaria diagnostic clinic. We found the controls, and we made sure that also the controls, of course, the controls were the ones non-pregnant patients who had chloroquine plus Primaquine. Yeah, we made sure that they didn't have any Vivax malaria in the previous 6 months as well. So in the end, we end up with 158 cases, which is composed by Primaquine untreated pregnant women, and 316 controls, which is composed by Primaquine treated non-pregnant women matched for them. And then we followed up all of them for 1 year. If some of them had Plasmodium falciparum, we were censoring, and we were also censoring then in the end of follow-up. So here is our first result, our non-parametric survival analysis. We could see that they are different, they have different curves, control and pregnant women. But okay, so we know from the beginning that Primaquine is efficient against, or efficacious against hypnozoites. So this curve is not saying much, but we posed 2 questions. How many Primaquine untreated patients do relapse? And also, how many Primaquine treated patients do relapse? We tried to answer these 2 questions with parametric survival analysis. So here, the simplest parametric survival distribution assumes a constant risk over time, and is just an exponential decay if the hazard is lambda is constant over time. Then we posed here our first assumption. We assume that hypnozoites is relapsing or is activating with a constant rate over time, and this rate is lambda here. However, not all patients are susceptible to relapses, just patients who had stored hypnozoites. Yeah, we expect that primaquine untreated patients store more harpnozoites than primaquine treated ones, but considering that it's not 100% efficacious, the treatment with primaquine, primaquine treated patients may also harbor harpnozoites. Yeah? So then here we posed our second assumption. A fraction P of the population is susceptible to relapses. Yeah? So considering assumption 1 and assumption 2, we can write our parametric survival function for the event of relapse as it's written here. So just a fraction P will be susceptible to relapse, and will relapse with this rate lambda, and the rest will not relapse. All right. But we know that we have a competing risk event here if we want to consider also new infections. Yeah. So one clinical event detected by the system can be a new infection, or it can be a relapse. Yeah. So how to deal with this competing risk of new infections and relapse? Okay. And we also have to consider that the risk is heterogeneous. Yeah, as we already saw. So around in this location, around 20% of the population is contributing to the majority of cases. So we cannot take someone from the high risk and the low risk and say that they will have a constant rate of new infections over time. So it means that the assumption of constant infection rate over time does not hold for new infections if we consider the entire population. So how is the idea here to overtake this? We can just select individuals accounting for their risk of new infections. Yeah? How should we do this if there is no index of the risk for each individual? So recalling that we had excluded patients who had one Vivax episode in the previous 6 months. Yeah. By doing this, yeah, we are just selecting, or we are claiming that we are just selecting individuals under low risk of infection. We are excluding all higher than average risk of repeated infections. Yeah, as we saw that graph where people is moving really fast from compartments. Yeah, we just saw that in the high risk group. In the low risk group, they are moving slowly. And then here, by doing this selection of patients, we can try to differentiate two different dynamics. Yeah, a fast dynamics of relapses, which is happening some weeks or months after the primary infection, and a slow dynamics of new infection. Because we are just selecting low risk patients, we are claiming that the rate of new infections is much lower than the rate of relapses in this case. We are not expecting that low risk patients will have many repeated infections over time. So then here, our last assumption, we are assuming constant new infection rate beta here over time, because we are excluding high risk individuals. Then in this case, we can use our parametric survival function accounting for competing risks. Yeah, as we said in the previous slides, what we have here, a proportion P of the population is susceptible to either relapse or new infection. The rest of the population, those who did not store the hypnozoites is just susceptible to new infections. With this, we wrote our survival functions for pregnant and non-pregnant control patients. We assumed here that a proportion P of pregnant patients who is susceptible to relapse is different than a proportion of non-pregnant control patients. And then we had two different survival functions. The only difference here is the proportion susceptible to relapse in pregnant and control patients. Yeah. Okay. Then, after the design of this model, we just fitted the model, and here we are seeing the results of the fit. Yeah. So the dashed line is our model, our parametric model, and the continuous line is the non-parametric, is the Kaplan-Meier. Yeah. And then because we did this parametric survival design, let's say like this, we can see that the non-pregnant patients, they do have relapse, but they have much lower relapse than the prima queen untreated or pregnant patients. Yeah. So, okay. And here we have some results from the previous graph. We could see that prima queen untreated patients, like almost 30% of them are susceptible to relapse. The prima queen treated is just around 12% in this case, around 12%, much lower than the previous one. But it's interesting that we could disentangle these and try to infer how many relapses is having someone who took prima queen. We could see that the average time to relapse or recrudescences here, I didn't mention, but can be either one or the other. But we expect more relapses due to the fact that there is not many cases reported in the area where resistant to chloroquine. Yeah. So the average time to relapse was around 46 days, and to the infection more than 1,000 days. And like this here with the values that we got, we were asking ourselves, okay, the rate of the infections, yeah, for both groups. So our inference, like can we be sure about this, or is just a mathematical exercise here? But then we look at the time to previous episode, yeah, and then we could see that looking back from the previous case, of course, here we started at 6 months before because we had this window. We could see that pregnant and non-pregnant patients, they were not different. Yeah, they were not statistically different. And if we plot our rate of new infections to the previous episode, like we are fitting really well this graph. So here we are inferring that we had little influence of pregnancy by doing this, and also we are kind of, let's say, confirming that the rate of an infection found in the competing risk framework proposed by our model is also fitting the previous one independently. Yeah, here I'm not fitting this, it's just the value used, it's just the value previously obtained. All right, then in the end, we simulated chemoprophylaxis of chloroquine being given over 4 weeks, 8 weeks, or 12 weeks, being able to suppress 6% of new infections, 80%, or 100% during the period of administration. Yeah? So by simulating this, here is the reference, the dashed line. We could see that chemoprophylaxis in pregnancy might suppress between 20, which is here, and 65% of the first blood stage recurrences experienced over the next 12 months. Then here, like the conclusions of this work, the selection criterion, which is the most important for our analysis here, it implies somehow like modulation among individual patients, like risk modulation, I'm sorry. We are just selecting low or mid-risk patients. We are excluding the high-risk ones. It allows distinction of the fast dynamics of relapses and the slow dynamics of new infections. And it minimizes the risk that the index case is actually a relapse. We started with this, but then we saw the other two. So our results agree with the most recent malaria treatment guidelines of the Ministry of Health, which recommends chloroquine prophylaxis since the first Vivax episode diagnosed during the pregnancy. And we are just saying that this framework can be applied for to different scenarios, such as clinical trials or prolonged anti-malaria stock outages. To estimate, recurrences and disentangle relapses and new infections, considering competing risks. So then in the end, last slide. So here in this work, we applied statistical, mathematical modeling, like survival analysis as well, to investigate the risk heterogeneity. And here the interesting thing, we were using real data from the transmission setting. Yeah, we are trying to fit, considering this risk heterogeneity, the models we presented here. To apply those models, it's important to mention that we need detailed data from well-designed cohort studies. Yeah, ideally individual level information. If we do not have this, we cannot try to make the inferences we did here. We also could see that the assumption of homogeneous population may be not violated when model is carefully designed and individuals are selected accordingly. As we saw in the last article, we selected all the patients selected. In the end, we assumed that they were homogeneous, considering the risk. Yeah, but it was just we could just make this because we selected accordingly. As countries move towards malaria elimination, there is this mention or this sentence in the WHO page. This is quite interesting to see. There is no one-size-fits-all approach. Like more target, regional, and age group specific solutions are desired as we are reaching or as we are moving towards elimination. And although the modeling exercise presented here used malaria morbidity data, we can use this, we can apply this for different infectious disease and even other areas of health. Yeah. Okay, so that was it. Here are the acknowledgements. So I had a PhD scholarship from CNPq, and we had all these funding agencies, FAPESP, NIH, and also had contributions from the other places as well. I thank the agencies and universities for this. Here is a picture there in the Amazon basin where I've been going since the middle of my PhD to make to collect new data, which for new studies, and is the same population that was considered in my study. They were really nice. Really, it was really amazing to visit every household, to talk with them, to know a bit about the forests, to know a bit about many things that I didn't know before, and to see a completely different reality than the one I'm used to in São Paulo here, for example. I'm really grateful for them to receiving us inside their places. Yeah. It was really nice. Here I'm just in a, this picture was taken in a place where they used to do this tapioca is called, yeah. And they offered me a piece, and like it was really nice, really tasty, having this with them. And here it seems that they are happy as well, showing what they were doing to us. I thank then here. So all the professors involved here, so Professor Gilberto and the Professor Stasinopoulos, who were contributing in the first article, yeah, like I learned a lot with them about regression analysis, and Professor Stasinopoulos is the one from the package, yeah, he was developing this package. Professor Antonio de Lima, Miles, Stephen and David, they were together with us in the last article, the survival analysis article. I'm really thankful for the very nice discussions. We started putting many distributions to try to model the risk and relapses, and then in the end we end up with a very simple and model that I really enjoyed to make. Yeah, it was really nice. They are co-authors in the article. Professor Gabriela Gomes, with whom I worked in the mathematical modeling. I really thankful for her. I learned a lot with her, especially like building very simple models. And she also received me there in the Liverpool School of Tropical Medicine. She just moved to another university now. Professor Jean, he was the developer of the package Pesto, which I used for parameter estimations in the second model. I just sent an email to him, and he received me there in Germany for 1 week to try to tell me some concepts about his package, and I learned a lot with him about parameter estimation. Really nice. And Professor Marcelo, who was involved in all the works I presented here. He introduced me to malaria research. He was really nice person during all the PhD. I'm really thankful. I consider now that we are reaching the end of this period. I have more than a supervisor. I have a new friend now. I'm pretty sure about this. And I could not imagine a better mentorship during this period. I'm really thankful for all that I learned during this period. So here many people from the lab, friends, and people from the field side. I'm really thankful for everybody that was discussing with me or just was close, not following up exactly the things that I did here, but supporting the ideas that I had in this period was really nice. They made this journey much pleasant as well. I'm really thankful for all of them. I met incredible people during this period. Thank you so much. And here, like, I'm really thankful also for my family, everybody who helped me a lot, supported me. Like, let me see, 7 years ago, I decided to create, let's say, more stable career as an engineer, to go back and become an underfunded student again, and I'm doing like this. I'm finishing this period right now, and they were really supporting me all this time. I'm really thankful. Yeah. Oh, sorry. And here I have my grandma. She's not with us anymore. Okay, so this is the last slide, and this picture was taken 3 weeks ago when I was there in the Amazon basin. So I thank you very much. Hope you enjoy it. Okay. Okay. Yeah. Oh, thank you. Oh, thank you. Hey, yes.
And today will help some other student, Marcelo, some other time, or maybe my students if I think about something like this. So let's begin. I need to follow here. I'll send you later if you want my PDF file with all comments and not very easy to understand because, but anyway.
Okay.
So I'm looking for my first comments. Just a minute.
Okay.
It's much easier when you have paper, isn't it?
Yeah.
But
So that's the reason I have it here.
the first question is, why did you use negative binomial model at the same time that you use the random effects model? Because you can model the extra dispersion at the same moment that you have random effects. So besides, it's the same question. I think I'm going to make a question and you can answer. It makes it easier. The same point is, did you compare the ZIMP model with the ZIP model? It may, and you have one less parameter and it might make it easier to understand the problem, because this theta that includes in the ZIMP model may not help. Because, well, anyway, answer it, and then I might discuss it a bit more with you.
Yeah, so I think we had this...
Some problem with your... No, I cannot listen.
No?
Are you talking? Sorry.
Okay, just a moment. I Can you listen now? No, you can't listen. Now? Yes? No? No? Oh, God. So,
que não funciona. Sorry, in Portuguese. I'm just complaining.
So
Rodrigo?
Oi, agora vocês...
Sim, sim. Tudo bem.
Legal, ok, tá. É porque foi comentado aqui no chat que não estavam ouvindo ninguém além de mim no YouTube. Mas eu acho que agora eu tirei o fone, todo mundo deve estar ouvindo, então. Okay, so I'll switch back to English and let's go. So the point is why we use it, the random effects, zero inflated negative binomial. So the random effect was due to the fact that people were living in the same household. So let's imagine that we have 5 people living in the same household, and we know that, for example, having a bad household, would add some common risk to all of them. So then, because of this, we add the random effect. The random effect was also considering unobserved heterogeneity. For example, spatial ones. If you are living, let's say, in one side of the city and they have higher risk, and there is another house in the other side of the city with has lower risk of infection in that area. The random effects should somehow account for this unobserved spatial heterogeneity as well. So then we started doing our modeling, comparing negative binomial random effect with random effects with the zero inflated negative binomial with also with random effects. But when we submitted this, in that case, the reviewer said that we are not adding much comparing 2 different models, then we just presented one as it is presented in our work. But yeah, I would say this, if we didn't consider the random effect, just the negative binomial, we wouldn't be including, for example, this unobserved spatial heterogeneity. I'm not sure if you are happy with this.
Thank you. I think that, well, I've asked the question because always when I try to use ZIP model and I compared with ZIP model, it was exactly the same result. And I think that that's why I've asked. And I think that your answer was quite complete about the random effect. So let me go a bit more. Right. When you included, it's another question, when you included the place, urban and peri-urban, I think it's now, urban and peri-urban, you kept the same random effect with another covariate, that's the place, is it right?
Yes.
So, when did you try to map what was left after you included the place? Because the random effect was taking into account this kind of stuff as well.
Yes.
Have you mapped the random effect after including the new covariate?
No, I didn't.
Try it.
Yeah, I think this is...
It would be interesting to have a look.
Yes, I do agree. We didn't have this idea by that time, but yes, it would be something really interesting to see.
Yeah, because you might have answered most of your unknown variables with this simple variable, well, peri-urban and urban. I don't know, but it would be interesting to map, and it would be interesting to see if this random effect is significant or not, because it can lose the effect, can lose significance. So somehow. It's just another idea, you know. I know the paper is already published. Maybe you keep going with the same study, the same data set.
Yeah, but I didn't went much in details about the selection of covariates we did. Yeah, because this is kind of technical and somehow boring. But like the random effects was always considered to be excluded as well. And even adding the zone of residence, like the center and the periphery, the random effects were still selected for the model. Yeah.
Right. Then you've answered this question. I just want to see the map. How is it now after you included it? I have another problem. It's a conceptual problem. If you have the nets and how do you call it? IRS, I think.
IRS, yeah, insecticides.
Yeah, the nets and this intervention. I don't remember the name. Intervention kind of.
IRS.
Inglês está dando nó no meu cérebro. Então, these two variables, they are associated with the risk, with the counts, but they might be people put nets wherever the risk is larger. So there is a kind of secular determination, you see. Yes. The nets are independently related to the counts, but the counts are the related to people putting nets over there. So there is a kind of, it's just conceptual. That's not a model question, but it's a conceptual question.
Yes. So what I would say about this, like we saw our results is saying that having bad nets or having the other intervention, IRS, it's increasing the risk. Yeah, our results is saying. But we know that it does not increase the risk. It's just because like I think we tried to discuss this in the paper. We know that this is just due to the fact that the policymakers are selecting some areas under higher risk and distributing this there. So then we saw exactly what you were saying. It's really interesting, and it could be tricky in some moments if we got this. Okay, we have bad nets and people are having higher rates. No, it's because they are
the opposite.
The opposite, yeah, exactly as you said.
Again, it's just an idea because to say that something is risk or something else, you are supposing that there's something comes before there's something else. Okay?
Yeah.
Or you have beautiful data, beautiful longitudinal data. You might explore it, because then you exclude this kind of reversal causality. You see, because you are going around. You see the tail.
Yeah.
So it's the suggestion to think about. That's things that popped up in my mind while I was reading. So I have another question here. No. Let's go to the second paper. I'm not going to talk about the second because I understand nothing about mathematical modeling, compartmental modeling. I love to listen to someone who understands it, but I have just questions. Again, really it's a question that because I don't understand it really. The main question is, let me find it. You used partial immunity, age as a proxy of partial immunity, right?
No.
previous immunity.
No. So it's like maybe someone with 50 years old that didn't have any malaria, he will not have any immunity. It's like the number of cases one has will be correlated with the partial immunity. So then this function, e to the power minus half I is the number of case or the number of previous case. It's somehow correlated with age, because we think or we expect that older people will have been exposed more times, but we are not adding straight away to the model.
Yes, I understand better now. But my question is, previous contact depends on the previous endemicity in the place.
Yes.
It's not. I don't know if it affects somehow where this modeling goes, because if you have high levels of endemicity, the previous contact does not. You see, it does not depend on age specifically. It depends on whatever was happening there a year before, 2 years before.
Yes, I totally agree with you. And in this model, we assumed that we were in a stable condition. That as I showed in the presentation, it was decreasing over the decades. But here is just an exercise of speculation. It's just speculation. I tend to think that the previous 10 years has much more influence in what we see right now than if we consider 50 years, since 50 years ago. Then in the last 10 years, we are more or less stable. So that's because I believe that the assumption of stable condition right now is fine. We assumed that. But I totally agree. I totally agree with you. If we were modeling like 30 years ago, we would have something different.
I have a problem with this kind of presentation thesis in articles, because we lose this kind of information that you are bringing now. How did you select the variables? I'm curious, and I have to ask. Because it's not written.
In which model?
No, I'm just saying that this kind of presentation, just papers,
okay.
It's insufficient for us to know what we would like to. Papers are very compressed.
Yes, I do agree.
Now, about the survival analysis.
Okay, let's go.
First question is, why did you choose a parametric and not a semi-parametric Cox usual model? But I'm asking this because we try to use parametric models when the risk is not proportional. And if you look at all your graphs, the risk is quite proportional. Kaplan-Meier and so on. So first question is, why parametric and not semi-parametric model, where you could include pregnancy, whatever, as a covariate, if the assumption of proportional risks is correct? You can test it anyway.
So okay, there is a lot of things to say regarding this question. I showed you that we combined the census data with the number of cases. However, for this study, we just used the number of cases. We didn't have information about the patient. We didn't have the household. We just knew the information that were in CVEP, which is the system that stores this information. Then we didn't have many covariates regarding this. We just had like age, sex, the place where it was diagnosed, and I would say more or less this. Then we wanted, in the end, try to disentangle both events, yeah, and we had the relapse and the new infection. I could not see how could we disentangle these with models that were not parametric. Like we consider this competing risk. We also had this competing risk, which is kind of trick to do with non-parametric analysis or other than parametric ones. Then we try to build this. We started, as I said in the presentation, we started putting gamma distributions and log normal distributions and all these kind of distributions, and then we were refining, and then we just went just finished it with the most simple parametric distribution. Like in the end, I think we, or at least we succeeded to answer the questions that we posed in the beginning with this parametric one. The non-parametric or other models, we would compare one with the other, yeah, and not things from the mechanism in which we included in the parametric analysis. Do you?
I disagree, but it's your choice.
Okay.
And I think you could do this then in a much simpler way instead of making all this parametric assumption, because parametric assumptions are very strong. That's why studying parametric in general is preferred, because it's not parametric in the risk distribution. But choices are choices. Yeah. I would like to discuss another possible choice.
Okay.
I think the way you've dealt with competition risk was very smart. You just exclude everyone that could be reinfection and not ACG of a right?
Relapse.
Fine. Relapse, yes, fine. But you could try to make it in different ways. It's just suggestions. Maybe you can do it. Now, if you count the number of previous episodes of the same people, you would be able to distinguish people that are in a higher risk than the people that, and then you could just estimate the effect, the hazard ratio of this number of previous infections and the whatever event that you have.
Yes, totally agree.
Think about it.
And we did this. Yeah, when we come up, like this was a suggestion from Professor Miles, which was analyzing this with us, and we did. But like we didn't have the sample size good enough to make this discretization, which would be wonderful if we had. But we just had 158 cases, yeah? With 158 cases, I would say we could do well. Low and high risk, or low and middle versus high, but we could not try to build the distribution. Yep. Yeah, but we did. Yeah, we did. It's really
That's why
nice.
I don't like this kind of presentation. You see, you should give us all the steps.
Yeah.
It's much more useful for someone who comes after you. Anyway, few more questions, just quick questions, I hope. Well, you analyzed time to first
relapse.
How do you say? Relapse. And then you've tried to do the second relapse. And you have a different, there you have a different baseline risk. If you look at the picture, figure 2, when you look at the second, the red lines, they are quite different. So you have really a different baseline risk. I think so.
Yes.
And then you have some, it looks like you have a different baseline risk because they're not at all parallel. So what I think could be done, again, suggestions, maybe your next paper, you could just use some kind of, it's semi-parametric, I preferred it.
Okay.
But my preference is not yours, probably. But you could just use this kind of model that you have time to event, first event, time from second to third, and you accept different baseline risks. It's a multiple event survival analysis.
Mm-hmm. Okay.
It's interesting.
Yes, but
you just think about, because then you can model. You don't have to assume any kind of function. You just look at it like, here is the one risk, and then the other one is here, and then the second to the third one, you have an order, the first to the second, second to the third, and this order organizes the different baseline risks pattern.
Yeah.
Again, maybe your next paper.
but let me comment on that. Yeah. So
Go ahead.
Yeah. So there in figure 2, maybe okay. In figure 2 of the last article, so it's page 8 from the last article. We had the second recurrence. Yeah.
Mm-hmm.
And here the things are kind of, let's say, in our view, or at least in my view, we cannot conclude anything here because of our strong assumption from the first model, which says that the first case, or the underlined case, should be a new infection instead of relapse. And to guarantee, or at least increase the chance to guarantee that the first case is a new infection instead of relapse, we are excluding people from having
6 months.
6 months, perfect. Here in the second recurrence, we cannot guarantee that it's the first case is a relapse or is a new infection, all this, Then here we just put as illustrative, or maybe to give some idea what could have after this, but we cannot guarantee. We don't have this assumption anymore. We lose the strength of our analysis, which says that we had indeed, or at least very likely, new infection instead of first case in the first analysis.
Yeah, again, you can model suggestions. You can model it using a frailty random effect for people. I think you could use it as an unknown variable that makes people have, kind of random effect for people in survival analysis. Mm-hmm. I haven't thought about it before. I'm just thinking it now, so I'm not sure if it's reasonable. But anyway, congratulations.
Okay, thank you.
Very good paper. Very good thesis for your PhD. Thank you.
I thank you for agreeing being here, and it was definitely a pleasure to have you here. I thank you very much.
I'm going to turn off the video and sound.
Okay, well, once again, Marília, thank you very much. It was wonderful to have you here again. Well, so for the next PhD student, we'll start with your suggestion regarding, yes, it's wonderful, the idea of mapping random effects after taking into account where people live. Well, that's a great suggestion. Thank you again. So now we go to Mercedes Pascual. Thank you very much for finding some time to examine this work. And now we go probably deeper into the second paper, I guess.
Yes. So yes, I'm sorry for that. This alarm. This never happens, but it was just a bad timing. So yeah, it's a pleasure to be here, and I will focus. I first should say it was a very nice thesis to read, and when I see a thesis that has 3 published papers, I also wonder why we are not really examining. We are kind of enjoying it. So it was a pleasure and very good work. So I will focus on the second. I think Marília had wonderful questions on the first and third. And this is where my expertise lies. My first questions are about the mold structure, the mold specification. I think I missed somewhere the complete expression for the force of infection. So you had your lambda 0, you had the age effect, but then the way the infection classes, in particular when you had infected and asymptomatics, entered or contributed to the force of infection, I don't know if I miss it, but I didn't see the equation. So you had lambda S, right? But lambda is the function of the I classes and the A classes.
Yeah, so like the lambda is age dependent, yeah? Age dependent force of infection. And then for the
So do you mean, okay, so that part I got, right? But the age does not, well, perhaps at steady state, are you saying that because normally in lambda you will have directly the contributions, right, of the I and A classes, right?
Yeah, okay, so I think I got the point that maybe is missing. Like usually most part of the models try to fit like prevalence data over time, yeah? Here we just have a picture what's happening.
Yes, a steady state. You are assuming a steady state. So you are equating age to the states?
Yes. Yeah.
Okay.
So age to the states, and then each person will move through the compartments like S0.
No, that I get. But for example, when you have infected and asymptomatics, at some point you said that you had a parameter for their contribution to lambda, right?
Yes. No, not for. Okay, not to lambda in the model, but it is for the contribution of each of them for the whole transmission. But this actually was not included in the model. So I just said that let's assume that asymptomatic person contributes half of one symptomatic, and then it's just arithmetic calculation. So
so you did not fit the model with those assumptions.
No. Yeah.
Okay. So that was a little bit why I was sort of expecting an expression that had those parameters.
To be honest, like it's not part of this PhD defense, but we did some other analysis right now. Like we will try to submit soon, in which we were considering not in a mathematical model, but then we were considering to the whole transmission this as well, and how they are affecting again the whole transmission. Okay.
I see. And so then the other question was about the asymptomatics, right? So you have the asymptomatics, and you assume that if you get infected as an asymptomatic, you transition to an asymptomatic infection, right? So the transition from asymptomatic with a contact or a transmission was to a symptomatic infection, right?
No.
Well, yes. If you show your graph, well, at least in the graph, that's the way it looks, right? You went from.
May I
Yeah.
just I just
sure,
select here because I had some place to write, because sometimes I like to write. Can you see? Yes.
Yeah,
okay.
perfectly.
So then S goes to I, and then this keep going, and then this comes here. A, this can come back, or this can go forward. So a susceptible can get infected, a susceptible can get asymptomatic, a asymptomatic can become susceptible again or become infected.
Yes, but become infected, it's at the rate given by the force of infection, the same force of infection.
Yes, the same.
And that's my question. So essentially, if you are asymptomatic and you experience, you don't have explicit mosquitoes, but you experience that force of infection, you move to I, right? You cannot continue being asymptomatic, right? So you are assuming that, so yes, you can lose your infection and become susceptible, but an exposure of an asymptomatic goes to I. So
yes.
it does.
Yes.
And anyhow, that's interesting. It's an interesting, because you could assume that you have the same sigma protection, and that with some probability, right, that you could stay asymptomatic rather than moving to I.
Yeah, you can, but like the underlying idea is like we are asymptomatic, and let's say you stay here, let's assume for now 30 days, yeah, and then if you do not get another infected bite to make you infected, to make you symptomatic, you become susceptible. And here in the susceptible, you are allowed to come back here. So
yes, I get it. I get that, but I'm just saying it's fine.
You mean like
I
a
just
loop?
think that yes, I think that you could do that, right? And it's just a question of why an asymptomatic that gets an infectious bite necessarily becomes infectious. Anyhow, it's a small detail, but it's an assumption. The other one is that essentially an asymptomatic infection does not count towards your immune protection, right? So the sigma counter doesn't, and that's an interesting
and I can discuss this, or at least I can add some comments on that. First, so we had this, we are saying that someone that got a bite is not coming here, is coming here because of the partial immunity. If he's already coming here because of the partial immunity, means that he somehow already saw that strain, which is not adding much to the immune system to add more partial immunity to that. And more than it. Okay, so let me just put here. Okay. Okay, so we have this, we have A, we have I, and we have S. Suppose that we move from here to here, from here to here. It means that in the next sigma, the sigma is going to be higher, yeah? And he's getting some partial immunity because of this. But we had a huge problem doing that. Actually, we break our head on that. If the guy is here, coming from here, I don't know anymore how many episodes he had, because our data set is just showing clinical infection, yeah, which is this guy. So if this guy came here, not from here, I'm saying that, supposing that here...
I see it, I see it.
Then I could not count anymore the number of cases per person.
I see. Okay. Well, it's fine. And the answer on being the specific strain is interesting, because, of course, your treatment of immunity is very much some sort of generalized immunity rather than a strain specific, right? So, but it's interesting to think whether it could be connected to strain diversity. Could you had something in the text that I guess I didn't completely. You had a certain treatment of what could be called a reporting rate, right? I forget the part of the text. It wasn't called that way, but maybe the question I would ask you is whether you have a reporting rate, because you talked about dividing the proportion of individuals by a factor. So individuals within I by a factor to represent the detection. So did you have so that part was a little bit unclear to me, and how you managed the reporting rate, and what was the assumption about reporting of the infectious clinical of the serious infections, let's say.
Okay, in this case we are assuming that we had all clinical cases reported, because we got the data from the Ministry of Health, yeah, and malaria is just reported under public clinics, and all cases are notifiable. And then what I did here, it was like this, yeah, S and I. But here I'm considering that the guys are here for 28 days because of treatment effect. Yeah, if they are taking chloroquine plus primaquine, in this case, they are going to be here 28 days, and the recovered rate is 1/28. But you see, the guy here is not 28 days infectious.
Okay.
Yeah, so I had to divide this, the sum, yeah, or the integral, the sum of i's for then I don't remember exactly the numbers, but to in the end, so I put a factor x here, to have 4, 8 or 12 days infectious, in order to compare the infectious from symptomatic with the infectious of asymptomatic.
Okay, I see. Okay. So maybe this brings me to the fitting of the model. And so I guess I haven't used pesto, but essentially it's once you have the function you are trying to optimize, right? You have your objective function. You did it in a Bayesian framework, if I'm correct, right?
Yes, yes.
And so I was wondering, however, about your model comparisons, because I didn't completely follow how many parameters were fitting and whether the homogeneous model had the same number of parameters. It seems to me already that you don't have x1 and x2, right? You have a single x1, etc. Yes. So I was a little bit confused by the presentation of the table of the likelihoods, the log likelihoods, rather than some other criterion to compare moles. And some of these moles, of course, could even be considered perhaps nested with some exercise that I didn't do myself. But I was a little bit surprising because I couldn't tell whether you could compare the likelihoods in that way.
Yeah, so essentially the only difference is what you already said, yeah? For the heterogeneous model, we had this, and for the homogeneous model, we had this, yeah? And here is 1, and here is x1, yeah? So this. And the parametrization of this distribution allowed us just to use, just to add from here to here, the variance, or from here to here, the variance, yeah? And then, because we had like, and then here we have P1 and P2. Here is P1 plus P2 equal 1. X1, P1 plus X2, P2. Yeah, okay, the mean is equal 1. The mean risk is equal 1. And then we have the variance, parameterize it with those values as well. And then, like, from here to here, we add the variance, but the variance comes up with another class, yeah, the high risk one. We were not comparing AIC values, but very likely.
Well, why not use some mole selection criterion, right? It seems.
I agree. Maybe it would be the best to be done in that moment, but we didn't do this. We didn't look different than the questions from Professor Carvalho. In this case, we didn't do this. I could have a look, but I would say the whole construction or the whole biological conception that we were studying was assuming that. And also we could see that the fit, okay, this is kind of subjective, but...
that was a little bit subjective, because although you said in the discussion of the paper that it was obvious that it was a very a very high improvement, I think you had the shape of the distribution, you were capturing it pretty well with the homogeneous model. So I think you need a currency of comparison, because the incidence curve was well captured.
Yes.
And there were some small differences in the distribution, right? So you need some, I would say, I would say that
it was a bit subjective, yeah.
That it was an easy step to take, and one that you could have taken, right? With your.
Yeah.
And
I agree. Maybe the AIC value, but sometimes we are adding parameters to our models, and adding this to the AIC would bring us some level of comparison. But here we are adding a distribution, yeah?
Yes,
This is in the same level. I'm not sure. But I do agree that an objective...
Yeah, it wasn't clear. I'm just saying, because I wasn't following which... if this was also the only difference in the model I was asking, because when I read the paper, I couldn't tell if it was the only difference.
Yeah, it's the only difference. Yeah, this.
And then, so it's interesting whether you have... you say that, of course, you don't have relapses in this model, and you had some discussion that they were implicit somewhere. I was not so convinced by that. And I was wondering whether from the numbers you get in the second part, or whether you could get a sense, because it seems to me, of course, that Vivax Vivax is notorious for relapsing, right? And many of these, and it's very, very interesting that the relapsing infections can also contribute to the force of infection, right? And
Yeah.
in particular with seasonal transmission and all that. So I know it would add a fair amount of complexity, but I was wondering whether you tried to.
Yeah, so
to
for this model we didn't, but I would say it would be really nice if this model was designed after our third article. Then we would have strong evidence to add parameters based on that. I would say now we could try to improve this model, adding explicitly relapses, but by that time we didn't have much information. How we are gonna say that? Okay, 50% of people is having relapse, 10% of people. Of course, we have data from the literature, but explicitly for this type of analysis, and also considering our third paper, like which is arguing for selecting patients accordingly for making regression, we didn't have the data by that time. Yeah.
Yeah, no, it's an interesting. Well, I basically had. I think in the thesis, one thing I think would be really nice for the conclusions would be to sort of comment a little bit more about how the three pieces, the three parts can inform each other.
Okay.
I think that would be really nice, at least for the future directions. Like what could you do, or what kinds of data sets? For example, I think if you were fitting them all to prevalence data and relaxing the steady state assumption, of course you wouldn't be fitting it to distributions. You may be fitting it to some other kinds of data. It may be very interesting to think, how would you use what you learn in the third chapter, maybe even in the first one, in regard to heterogeneity, to how you would construct a transmission model and explore some of these issues. I sort of missed a little bit that in the, like if you had, with all you learn, what would be the next steps to bring some of this together?
Okay.
So that would be really nice to see. And yeah, in relation to that, I wasn't so convinced by the steady state assumption argument. It's of course very, very justifiable in light of the data you had, but of course there are some very nice approaches for fitting models to time series, and it's interesting to think, if you had this distribution at some times, but you had longer incidence data, could you attempt to fit a model and perhaps relax the steady state and so on? I think those are worthwhile directions.
Yeah. It would be really nice to have data to make such analysis, but with the data we had, we could not go in this direction.
No, it's true, but you have the incidence, right? So you have the incidence going back for this region, or
we had like the
incidence with age. I see the total incidence.
Yeah, the total incidence. Yeah.
I see. Yeah. Well, but you could. I think you could advise perhaps the data collection for the future.
Okay.
Like how could you perhaps now, if you had to say, what would you do better if the data could be collected in different ways? I think that would be a very worthwhile contribution. So yes, so I guess yes, I think it's a very nice model. I think I wonder, of course, the data probably wouldn't support more than 2 classes, but it would be very interesting to see if you had a distribution. I don't know. So let me finish, just because others may have more questions. The chapter 1, I thought the peri-urban versus the center of the city is very, very interesting. Of course, we know this issue about malaria, except for India, where there is truly urban malaria, right, with a different vector. So that then when you become more urban, but it's interesting what is more urban in the Amazon, right? So it's very interesting to see this pattern so clear, right, with this distinction. Did you try to see whether, if you wanted an explanation for the peri-urban, which of course could be just, the typical explanation.
Yeah, so there is maybe if I can, maybe if I share my screen, it's okay.
Yes, yes, yeah, unless there is a rule against it.
Let me say it. Okay, so okay. Okay, so let's just here. You see my presentation, right?
Yes.
Okay. It's here. Okay, so this is the city, right? Two things I would say. Yeah, we had the forests here in this area. We also had forests there, but less vegetated. But look here, we had many fish tanks, fish ponds.
Yeah, the fish ponds.
Yeah, all around the city. Look, here. This may be one of the explanations, I would say. Yeah, so being the surrounding of the city, maybe you are closer to the forests, and maybe you are closer to larva habitats.
Yes. So yes, those are because it's very interesting the way urbanization grows into the forest, and I was wondering whether your study could shed some light about the risk factor. This distance from forest, density of fish ponds, times in settlement if you had some geographical pictures of the city, some sort of time since transformation of the land, which has been a very big factor in explaining how this nonlinear risk in time with deforestation. So I think it would be, perhaps in your nice regression, you can add some more to that. Yes. I mean, to whether it's just the peri-urban or it's something about the peri-urban environment.
Yeah. Definitely, it would be really beautiful to do this. We had some conversations at the beginning. We could try to map and add the distance between households and these fish ponds and so on. But in the end, it's really difficult to define all of them. They are changing over time because people are just living then. And there is also this characteristic that fish ponds that, if well treated, I mean, like if they are cutting the borders properly, they are not an habitat for the mosquito. And then we could not see this from satellite images. Yeah, it would be difficult to, maybe we could have some bias if we try to add this, and then we just have this differentiation.
No, I was curious because I've read some work in that area, and it's interesting to know, time since deforestation, distance to the forest. I mean, some of the factors. Anyhow, I think I'm going to stop there because there are other people that have to ask questions. And as I said, I think the work is very clear and very nice. So I would, anyhow, I think I can stop for now.
Okay, so I thank you very much for accepting this invitation.
My pleasure.
Okay, well, Mercedes, once again, thank you very much. Well, lots of quite interesting questions. I would just mention that actually malaria control people in the town where we work in Marília, they have already mapped the fish tanks. But as Rodrigo said, there are a few other variables. I mean, some of these tanks are maintained for a while and then they are empty. Not all are real mosquito breeding sites. But I do agree that this finding of real urban malaria in the Amazon is fascinating. It's exceptional. It's not what we see typically in Amazonian cities and towns. And the point here is that the same kind of phenomenon we have in Marília is also common in the periphery of big cities like Manaus, Porto Velho. So it's not just a curiosity, it's something that may just explode in big cities in the Amazon in the near future, including Iquitos in Peru. In the outskirts of Iquitos, there are lots of fish ponds that can become very productive mosquito breeding sites.
Yeah, well, it is an interesting question because there is, well, at least some of the work I have been involved with, how from the time of deforestation, well, you know, the work of Marcia Castro, but it's very interesting. You could consider it some ecological changes to the vector, but I think there is these very particular types of land use change that are associated with the Amazon, and understanding some of this, what we call urbanization in places like Acre versus the bigger cities. I think it's very, very important, and how this changes over time. So there is something about the age of the land that has been deforested. So those are all things that perhaps in Acre can be understood further.
Sure. Once again, many thanks. Now we go to Claudio Struchiner. So Claudio gave us the pleasure to examine Rodrigo during the qualifying examination. So he's very familiar with most of the work presented here, and I'm very glad to have Claudio again assessing the final results of Rodrigo. So Claudio, thank you very much. So it's yours.
So I would start by thanking Rodrigo and Marcelo for the invitation. It's always a big pleasure to be interacting with your group. I always learn a lot from this interaction, and as you mentioned, I had this opportunity to be exposed to a preview of Rodrigo's thesis. Actually, I had two opportunities of being exposed to his material. One was during his qualifying, and the second one was during a mini symposium in which the Australian group came to Brazil. And in this previous interaction, we had the chance to chat about alternative ways, approaches to deal with heterogeneity. At that time, we mentioned about the frailty models, the Vopel work, and it's very good to see that this has been accommodated in the approaches that he finally took to analyze the data. I don't have much more to add about this malaria discussion, since Rodrigo was thoroughly interrogated by Marília and Mercedes. And what I would like to bring is probably a follow-up to this previous discussion on ways of modeling heterogeneity, and try to ask the question why to model and what we can do with heterogeneity. Some of those questions came up, were raised both by Marília and by Mercedes. So they touch in issues like reverse causation, time-independent confounding, and things like that. So malaria is very, very tricky since the time of the dependent happenings description that Ross came up with, attributed to describe this complexity. And since then, it was very clear that we are not dealing with a homogeneous occurrence of a phenomena, but we are dealing with something that those indirect effects mess up with the causation, the final causation of the in which we could express what is going on. Okay, so then the issues that I would like to bring are issues related to the causal interpretation of what you are doing, and of course to try to come up with a sort of a directed acyclic graph that could somehow provide us a rationale for this discussion. So the way that I see things is that heterogeneity is sometimes being addressed as an extreme way of have his own stratum, and this is materialized either by a Freire model or by a random effects model. So each unit of observation would be assigned to its specific stratum. And the regression or the analysis aims at describing the drivers. You actually use this expression in paper one, the drivers of heterogeneity. And when you do that, you also have implicit this intent to manipulate those drivers, which means that you see them as the causal mechanism for the heterogeneity that you are observing. Okay, actually, you are not observing. This is another interesting point, because it's not a stratification that you stratify in an observable variable, but it is a stratification that you come up with by means of your modeling approach, okay? And once you obtain this stratification, then you try to go back and see what are the implications of the stratification to the interpretation of your data. So you didn't have the population or the units of observation stratified beforehand. You didn't know anything about what would be your random effects assigned to each unit of observation. but you do this, so the stratification is actually an outcome of your analysis, is the dependent variable in your regression, and so it depends on what you put on the right-hand side of your regression, okay? So you are explaining the random effects by means of the variables that you have in your right-hand side of your equation. So sometimes you see it like that, okay? So then what you are offering us is a stratification mechanism adjusted by the variables that you have in your model. And sometimes you see the stratification as the basis of the causal mechanism that you want to manipulate in order to control transmission. Because you are going to say, oh, if this guy or if this unit of observation is under a high risk regimen, then I'm going to manipulate that. I'm going to come up with a control strategy that will address those individuals and somehow eliminate heterogeneity from the environment, okay? So if we do this, then we have to see how we choose, how we design our experiment, and how we choose the variables that we are controlling for, that we are entering in our analysis, okay? So when you are adjusting for a variable, and when I say adjusting for a certain covariate, I'm saying that I can do this by having this variable in my model, or I can do this by an actual stratification in which I have two more strata. So when I do this, I am under a problem known in the literature as confounding or Simpson's paradox, okay? So the idea is the association that I am, the implications that I am describing could be real, or it could be the artifact of some confounder that would be acting on both variables, the stratifying one and the outcome one. And the question that we have to answer is, do we want to report the stratified result that we have, or do we want to report the summary result that we have in mind? The second issue is the issue of a collider, okay? Is when I have one covariate in my model and I don't want it to be in my model because it will induce an association that is not there. So this is a situation in which I would have this collider being the outcome of my stratification variable, for example, and my outcome, okay? So what I miss most in your discussion is how do you see the causal structure in what you are trying to model, okay? So what is the role of heterogeneity? What is the role of random effects and frailty as a driver, as a cause, or as the outcome of other causes that you are trying to deal with. So this is extremely difficult since you have genetics, you have immune response, you have environment, you have social components like behavioral components. So I don't know what is confounding what, and I don't know if what I am using as a variable in my model or my statistical model or my ODE model. So I don't know if it is a collider that is messing up with all the relationships that I have. So I remember when we were in those two occasions in which we had this opportunity to interact about this kind of modeling strategy, that having a model that fit the data is not the end, it's just the beginning. So no one wants a model that does not fit the data, okay? Mm-hmm. And once we have a model that fits the data, then we have to consider alternative ways to explain what we are seeing, so we could address the issues that I just mentioned. And I missed that a little bit, because you stop at the point when you had a model that fits the data. You are happy with that, okay? And you do not confront the models that you just were able to conceive, and that you were able also to make it fit the data with other alternative ways of explaining the observations that you have, okay? So I guess I would stop here. I don't have any further comment beside this one, but I would like to see what are these causal structure, how you can deal with reverse causation that Marília mentioned, how you can deal with time-dependent confounding, which is this successive, this longitudinal way in which the immune system deals with new exposures, and the lack of exposures also when you lose immunity. So this is a big problem since McDonald's came up with this idea of super infection. In his mind, it was being exposed to more than one infection. And the model that he conceived was wrong. So the description of the model was one, but the math of this model was not following what is being described in the words. And then Nadelman came and wrote this whole stuff following the explanation that he had in words about the superinfection. So I stop here, and we'll leave you with this question.
Okay, so it's always a pleasure to listen to you talking about, let's say, not mainstream things. Yeah, I really enjoy this, and I do agree with you. I do agree, but so I will try just to once the work is like that, yeah. But I will try to make a conversation here, okay, about this point. Once we had the models and we fitted the models, yeah, I would say, yeah, we were happy with this, but it's incredible how could this go further and confront causality and what we are seeing, and what is effect or what is causal, yeah, about all this. In my mind, just trying to to discuss this, I believe that, not that I believe, but all the models are simplifications of reality. Yeah, we know this with no problems. And I would say we were not able to discuss, or at least I think right now that we were not able to go deeper on these kind of discussions that you are bringing to us. And I could say that if with the models that we developed, if we try to make different other models, also feed the data and see the same history from different points of view, I think from this point we can try to initiate a discussion about what is causal or what is consequence or what is effect. Yeah. Because it's really difficult for me just thinking after your speech that one could make a model and discuss what is causal and what is effect by if you don't have, let's say, decades. Yeah, you need, in my view, yeah, you need work on the top of work, on the top of work, on the top of work, and then perhaps we can make some stronger conclusions about what is causal and what is effect. I don't see how we could go further in the type of analysis we did. Maybe somehow, and this is a criticism about my own work, maybe we were not that deep, yeah, or we were not that deep. This is an affirmation. And I, as a modeler, and seeing the things as Professor Carvalho just said, like trying to viewing the points from many different perspectives, I think in the end of my career, I'll be able to make more strong arguments about what is causal and what is effect. Right now, it was incomplete.
So I hope to see a DAG in the next opportunity that we have together, a DAG that would have heterogeneity as one component, to see the role that it plays in this causal structure, and also that it
I'm not listening right now.
Hey, it's Rodrigo. Oh.
Eu acho que o Claudio congelou.
Sim, eu também não estou ouvindo.
Claudio congelou.
That's the curse of online meetings. But anyway, this happens. Claudio, so we can't hear you right now, but please feel free to interrupt us whenever. So I see John is still here. So John, if you want to make any comment, please, that's the time to do it. And thank you again for agreeing to be here to listen to what Rodrigo has been doing over this last few years.
Marcelo, I am back. Let me just finish my last sentence.
Ele não vai conseguir terminar. Cada vez que ele tenta terminar, ele trava.
Please, Claudio.
Am I back or not?
Yes.
Yes.
Okay, so it's just one sentence. I'd like to congratulate you and Marcelo and your co-workers and all the research group for the amazing work that you did. It's really amazing. It's excellent work. And the issues that I brought up, it's just for us to have fun and try to deal. So those are issues that are buzzing in my mind, that are keeping me busy in trying to see how we can accommodate evolutionary process in a context of causal inference. Okay.
So,
thank you and congratulations.
Thank you. I thank you very much. As you said, in the other two opportunities, I learned a lot. I learned a lot right now, and this is really like sentence that is stamped on the soul, you know, like it's things like this I will take for the rest of my life. Thank you very much.
Okay, so thank you, Claudio, once again, and John, thank you again, and please.
Yeah, well, thanks for inviting me, and it's really it was really fun to see your presentation, Rodrigo, and also to hear the feedback from all of the committee members here. And it's clear that you've done work and also had really good mentorship guidance along the way as well. It's a good group of collaborators. Yeah, so like Mercedes said, all your work has already been peer reviewed, and also it's already been thoroughly, grilled on this call. So yeah, I won't ask too many questions, but there are a few things that I'm just curious about. And as mentioned by a few of the others, I'm really impressed with the range of techniques using to approach these problems, using the statistical, the mathematical, and survival analysis, and then of course there are other approaches that you could explore as well, which would be fun to look into. One thing that I was curious about was the Plasmodium falciparum versus Plasmodium vivax. I think in figure 2 of your in your introductory section, it looked like over the years the falciparum has reduced in prevalence, but is maybe still present to a small degree, like maybe less than 10%. Are the cases that form your data, do they include falciparum, and is it assumed, do you have data on whether they are falciparum or vivax cases?
Yes, I had, and in the first study, we modeled all the case. In the second and third, we considered just vivax. And yeah, vivax was also reducing, but falciparum was reducing more over the years, especially because Brazil introduced the plan for malaria elimination and was focused on falciparum. Yeah, of course, vivax takes advantage of this as well, but they were focusing on falciparum. Right now, we have, correct me if I'm wrong, Marcelo, but I think falciparum cases are still growing again in Brazil. Yeah, and usually is like that. We have 85% vivax and 15% falciparum around the country.
I see. So in your statistical model, did you, in the work that you presented and published, is that only vivax cases, or does it include falciparum?
The statistical modeling, both Vivax
Both.
and falciparum. And the other two, the mathematical modeling and survival analysis, just Vivax.
I see. Okay, interesting. And then the two of them are included in the same outcome variable as the incidence.
Like okay, in the first one we had all of them belongs from to the same data set. In one we just extracted the number of cases per person. The other one we disentangled the same data set into number of cases per person and incidence data or incidence data stratified by age. And in the last one is the survival analysis, just Vivax from pregnant patients and matched controls.
Interesting. Yeah, I'm just curious about the relative burdens of the two, and I imagine the Vivax is more difficult to eliminate because of this. You know, it hangs around for a long time and can relapse. And are there any findings from your work, perhaps with the comparative study of the two, that could lead to interventions or that could help inform control programs to target one or the other?
In the end, we just had general conclusions which would be applied for both, I would say. So in the first one, targeting, we are okay, so I'm kind of insecure to say all these things about after Claudio speech, but let's go. So we know now some risk factors, and then we can target high risk populations. But we also know that the asymptomatic compartment is important for the ongoing transmission. So because of this, here we have two different strategies. Yeah, in the first one, we know where they are, or we know who they are. The second one, we don't know who they are, and we have to search. Yeah, and okay, there are different strategies, and we didn't test or simulated any of them. But I would say, for example, if we know that the high risk individuals are contributing more, and they are the ones asymptomatic, but eventually they become symptomatic, or vice versa, I would say one strategy to focus, like if you know someone who had malaria at a moment, this guy should be targeted. Yeah, we saw that during 3 years, or almost 3 years, around 60 or 70% of the population had 0 case. So then one thing to follow is people who had some case. Yeah, if they had case, very likely they will. Okay, the probability to belong to the high risk compartment is higher, and then you can, considering this, you can try to search for the high risk people. Also, we are suggesting chemoprophylaxis for pregnant women. This is really important once our group as well is already saw and is also studying this. Like babies or the fetus, I'm not sure if this is the correct word, but is having problems if the pregnant patient is having repeated case of malaria. There is increased anemia and other problems related with the fetus. So chemoprophylaxis, especially considering chloroquine, is really important in this sense.
Interesting. Yeah. Actually, something I was curious about with the mathematical model was the chemoprophylaxis, and it didn't appear to me that was included in the model, from S to I. with your asymptomatics and then subsequent infections. Would that be imagining, say, the recovery as being the result of either treatment or recovering without treatment, some average of the two, or if there are a majority of cases in which there is treatment, so you just assume that?
Sorry, I didn't get the question. Is like, so could you just repeat, please? Sorry.
Or with your mathematical model,
yeah,
how was treatment incorporated into that?
Okay, it was not. it was not included. We just estimated the force of infection. So the force of infection is giving the probability to move between compartments. And we have here, like, the first line treatment, at least for Vargas, is chloroquine plus primaquine, and for falciparum, I'm not sure the treatment for falciparum, but it's like the majority of people is having the same treatment either for one or for other case. So it's kind of homogeneous in this sense. It's not homogeneous in the sense that some people is not taking it completely, some others are taking it completely. But I didn't include the information from the third article into the second article, mainly because it was timely inversed. Yeah, the first came first. No, actually the first came first, then the second, then the third. If we had done the third before the second, we could improve the model definitely, as I discussed it with Professor Pascual. But at that stage, we didn't have strong evidence to add specific things about treatment or relapses or this kind of thing.
Yeah, I think you did a really commendable job of working out a parsimonious mathematical model that could that had enough parameters that were identifiable to align with that data set. Definitely a challenge, and there are malaria models that are more complex, that incorporate more detail, with the treatment and the immune status. Asymptomatic versus symptomatic, but those will incorporate a lot more, data, perhaps across a regional scale, and you didn't have that available here. So I think that makes total sense what you did there.
And just a comment on that, what I really enjoyed in the mathematical modeling was the fact that all parameters were estimated. We didn't take any of them from the literature, but the asymptomatic recovered rate, which was the one that we tried different values. But all the others was based on data from the locality. Sometimes I see models like getting data from here, from there, from other places, even different vectors or different plasmodiums, and combining the same. Okay, sometimes this is really reasonable, sometimes not. In our case, we got all the parameters estimated with local data. I really enjoyed this.
Yeah, that's really impressive. Yeah, it's a really interesting study, and I've seen some, I guess, fitted models for Plasmodium falciparum for some of these parameters, with the asymptomatic versus symptomatic, and some of the immune functions. But vivax can be quite difficult parasite to model due to this relapse biology. So to take that challenge on and do so in a parsimonious way is no easy feat.
Yeah,
So yeah, congratulations. I'll leave it there actually because yeah, I think we're close to the 3-hour mark here, and you've had a lot of questions asked of you, and I think you know, answered them very well. So yeah, I really enjoyed that. It's great having such a huge, varied toolkit available to you to address a range of mathematical and statistical problems, and you know, to address them in a parsimonious way, and with you know, a variety of collaborators. So so congratulations.
Okay, I thank you. I thank you very much as well, John, for being here, and yeah, so it was a pleasure for me as well. Thank you.
Okay, well, again, John, thank you very much. It was a pleasure to have you analyzing this results, this material.
Maybe just quickly also thank you everyone for speaking English just for me. Like, I'm sorry to be the one person who doesn't speak Portuguese, but I appreciate that it was nice to be able to understand everything everyone was saying.
Thank you.
Thank you very much. And so, Claudio, Mercedes, and Marília, we will move. I sent you an email with another Google Meet link. This is the one we use for our meeting right now. It's just a formal thing that we have to meet and decide what to do with this guy who just spoke to us. And then we get back to the same meeting now. So you can keep it alive, and we just move to the new one. Did you get my email, everyone?
Yes, I did. I just have a question. So we exit this one, or you said keep this alive? No. Okay.
No, we can keep it alive. We don't need to exit. We just mute it
okay.
and move to the other one, and then we get back. Okay? I think it's easier for everyone. And how did you get the email as well? Great.
I am having.
Excellent.
I guess I'm still here, Rodrigo, but I'll sign out. But congratulations! It was really cool to see your papers presented in detail. Like it's somehow it's much easier to understand things when someone's talking you through them than just reading. So
yeah. So yeah, it was nice in the beginning.
Oh, I think you're muted.
Oh, sorry. Oh, okay. So yeah, it was nice in the beginning. I think I was a bit nervous because the presentation was not going on, and I didn't realize.
Oh, yeah, no, that was.
Yeah,
it was
okay.
funny.
So
it was funny.
Yeah, I thank you for being here, John. Really nice. Yeah.
Yeah, no, it's really helpful for me to understand, what you've been doing, and yeah, there's definitely some contributions I think that we'd really benefit from with some of this data we have in Sao Tome. Similar malaria incidence data. Actually, probably.
John.
Oh, yeah?
This is Mercedes. Sorry, you need to move to the other meeting because we are hearing on two places.
No, it's okay. It's okay.
No worries.
We will come back to Rodrigo. That's what I understood. I don't know.
Oh yeah, I think am I supposed to come to your meeting, or it's just you and the other meeting, right?
I think I understood you have an email with another address in that you need to go to that link, right?
We are already there.
Yes, we are there, but he's in the other one.
Oh, I think I'm an extra person, so I don't. Okay, I don't know. I don't have the email. But I'm an extra person, so I don't need to be in the other one, right? So
Yeah, I don't think so. But
yeah. So and I think they can all hear me. So yeah, just let's catch up another time soon.
Right.
Once this is all over and you get the result.
Great. Yeah, sure.
Okay. See you later.
Okay, see you.
Now Rodrigo disappeared.
Yes, he disappeared. By the way, oh, the sound is not very good. Okay. No, it's funny because I understand Portuguese perfectly, but I haven't spoken it for a very long time. So otherwise you could switch. I mean, you can switch to Portuguese if you like. You don't speak in English for me.
Sorry, I made a mistake here, but it's interesting. Well, I just waiting for Claudio. Yes, great. Claudio's back, and then Marília. I'm not sure if John is coming back. No,
No, he left. Oh,
Rodrigo, you're muted.
yeah, he left.
Okay, So we had a very let's say
heated discussion.
Exactly. And after that, we realized that it's okay. We can give you the PhD degree in something very mysterious, which is called biology of host cell relationship, host parasite relationships, which is essentially everything. So, Rodrigo, congratulations, and thank you, Mercedes, Claudio, and Marília, for the wonderful assessment you did. And just a very brief comment about Rodrigo before I leave. I mean, and I sent by email to you also a sort of certificate, just attesting that you participated in the thesis defense. I have some paperwork to do, but it's essentially I'm usually signed for the members, the panel members. But anyway, I will send you copies just to be sure that I did the right thing. But just a couple of words about Rodrigo. As you can imagine, I am a medical doctor, but I'm not like Claudio and Marília, who actually were able to learn those difficult things about mathematics, etc. So actually, Rodrigo took a very risky decision when he came to our laboratory here to get his PhD degree. And the whole story, which is not told in the thesis, that Rodrigo was in Europe at that time, and he was considering he had just finished his master's, and he was considering going to Liverpool to study with Gabriela Gomes. But at that time, there was no scholarship. There were some issues regarding her to get accepted in Liverpool, support, etc. And then I suggested, well, what we can do is, one of the nice things about our graduate program here is that it's very flexible. So the students can come here, they can study wherever they went. They don't have a fixed course schedule. They can take courses in mathematics institute or wherever they went. So I said, well, this is flexible. I guess you can get training at the university. But the point is, I can provide a very specific training in either modeling or very or more sophisticated statistical analysis. And having Gabriela, Miles, and a few other collaborators working with Rodrigo all this time was very important for him, because alone I wouldn't provide the necessary feedback and the necessary support for him. I must tell that Rodrigo came, as a modeler, he came very well trained from different sources, both in the academia and also in the industry. So he had two different kinds of experience with different kinds of models, and this was very, this made things much easier for me and all the collaborators who were involved in this training. And finally, Rodrigo became also a field person. So in addition to working at the computer, Rodrigo has been helping us in field work. And as he said, he just came back from Acre. We did a cross-sectional survey between April and May, and he spent 1 month there, not only doing real household visits and also troubleshooting data entry and all the stuff. So he became a very, very valuable member of our laboratory, not only because he is the most skilled computer person here, but also as a leader in field work and many other areas here. So it was a pleasure to have Rodrigo here in the lab for the past 4 years. I hope he in addition to going to the Amazon and things like that, I hope he enjoyed staying here. And again, I thank you very, very much for your attention, for your work analyzing this thesis, and thank you again.
Yeah.
Rodrigo, would you like to say something?
Yeah, so
can I, before you say something, can you also tell us what you are doing next? What are your plans? I mean, conditional on having passed today.
No, sure. So, yeah. So, just answering Marcel, it was definitely a pleasure to be here in this environment. As you said, like, we could do whatever we want as soon as we accomplish, like, the number of credits. Talking with Marcelo was always, like, I was learning a lot about, like, just learning a lot, no, just learning a little in my case, yeah, about immunology, about genetics, about field work, about epidemiology, about all this kind of things. Was really, really a pleasure, and I thank you, Marcelo, and all the other members of the lab. I thank you guys a lot. Thank you very much. So just answering Professor Pascual, yeah, so I'm moving now. I'm gonna do a postdoc. I'm gonna work with Marshall there in UC Berkeley. Yeah, so I start there in July if everything works well with the visa, because like COVID is, yeah, unpredictable in this sense. So this is what comes next. Thank you.
Berkeley to Acre, I think it's as far as Rio to Acre.
Yeah, and I learned that in Acre there is a city called California, right, Marcelo?
Yeah, very close.
Yeah. Yeah, really nice. Thank you.
Claudio, you're muted.
Keep in touch.
Yeah, sure. I will.
Send us news and tell us about the good news.
Okay, sure. I will keep in touch.
Okay.
And I always joke saying that now you can see what happens in those closed meetings after the PhD presentation. So you're going to see that we are just talking about soccer and all the Argentinians and the Brazilian teams, and about São Paulo and Palmeiras and things like that.
Yeah.
Which is a good topic, by the way, because I support São Paulo. So. Okay.
Well.
Okay.
Well, anyhow, I hope we get to see you when you are in the US. Maybe at the annual EID meetings or something like that. So it will be very.
Yeah, I will be there in the EID. Yeah, like we had work that was just approved. So yeah, definitely, it will be a pleasure to meet you there. Thank you.
Okay, well, congratulations for a wonderful piece of work, and very nice to see everybody. And Marcelo, very good work. Thank you.
Okay.
Bye bye.
Ciao, ciao. Ciao.